previous session, we look at non-homogeneous equations. That is non-homogeneous integral equations. Y of s to be equal to f of s plus lambda integral from a to b. K of st y of t dt. It's not non-homogeneous because the function y of s is not equal to 0. But in this session, I'm going to focus on homogeneous integral equations. So that is y of s to be equal to lambda integral from a to b. K of st y of t. Y of s is equal to 0, which makes this equation to be a homogeneous integral equation, since the unknown function appears under the integral sign, as we explained in our previous video. And since it's a homogeneous integral equation, it has a trivial solution. That is y of s equal to 0. It's always a solution to this integral equation. And in our previous video, we said that the values of lambda for which y of s is not equal to 0, that is the non-trivial solution, lambda becomes the eigenvalue. And the solution, the non-trivial solution, is the eigenfunction. So I'm going to learn how to solve for the eigenvalues and the eigenfunction when given a homogeneous integral equation. So given this equation, the homogeneous integral equation, y of s, which is equal to lambda integral from a to b, k of st y of t dt. Let's assume that this kernel is separable. Let's assume that this kernel k of st is separable. That means you can separate it into two different functions, which is equal to g of s, then h of t. Now let's substitute this g of s and h of t into this equation. We are going to have our y of s to be equal to lambda integral from a to b, then g of s, h of t, g of s, h of t, then y of t dt. And g of s is a function of only s and does not depend on t. The integral sign is respect to t, so it's a constant inside the integral sign. So why don't we factorize the g of s outside? So we are going to have y of s to be equal to lambda g of s integral from a to b, then h of t y of t dt. As we are doing in the exact method, we represent, if we integrate this, it's a paradigm to g equation, so a to b. If we integrate this, we are going to get a constant for this. So why don't you represent this side by a constant? So y of s, so let c to be equal to integral from a to b, h of t y of t dt. So let's substitute this c into this equation. So our y of s becomes lambda g of s c. So this is the eigenfunction. If only this is the eigenfunction and lambda is the eigenvalue, which is a constant. So if we are able to solve for the lambda, that's the eigenvalue, then you are able to compute for the eigenfunction for the eigenvalue. Now we said c is equal to this y of t, and so let's interchange the s here to t's. So y of t is the same as, then lambda, let's bring lambda c, then g of what? T. And you have to substitute this y of t into this equation. And we're going to have our c to be equal to integral from a to b, then h of t lambda c gt dt. Then lambda c is a constant, so we can bring it outside. So c is equal to lambda c integral from what? A to b. Then we're going to have our a to be h of t g of t dt. Now let's divide both sides by what? C. So here the equation becomes 1 to be equal to lambda equal from A to B, h of t, g of t, t. Now we can solve for what? The eigenvalue here by dividing 1 by this integral. So our eigenvalue becomes 1 divided by integral of A to B, then h of t, g of t, dt. So since you are able to solve for this eigenvalue, and you can easily, since here is a constant, here will give you a constant because this is the same as lambda is the same as a constant. This is the eigenvalue. So if you substitute this eigenvalue to this function, this one becomes the eigenfunction, and this is the eigenvalue. Now let's look at one particular example under this and for better understanding. So in this example, y of s minus lambda integral from 0 to pi over 2 sine s sine t, y of t dt equal to 0. Show clearly the eigenvalues and the eigenfunctions. So we can rewrite this equation as this is solution as y of s to be equal to lambda integral from 0 to pi on 2 sine s, then sine t, dt. Now there's no free term here. The f of s side is equal to 0, so you can easily see that this equation is a homogeneous integral equation, and it's from 0 to pi on 2, and pi on 2 is constant. This makes it to be a Fredholm's homogeneous integral equation. Now sine s is a function of only s, and the integral sign depends on only t. Then this sine s is a constant, so you can easily bring it out of the equation. So y of s becomes lambda sine s, the integral from 0 to s, 0 to pi on 2, then sine t, y of t dt. This, if you evaluate this integral, you are going to get a constant. So let's represent here by a constant c. C is equal to integral from 0 to pi over 2 sine t y of t dt. Now this equation becomes y of s equal to lambda sine s, then the whole of there is c, so times c. If you are able to solve for this lambda, then this becomes our eigenfunction. So we are having y of t here. Let's change the s here to t's. Now here becomes y of t is equal to lambda c sine t. And now let's substitute this y of t into this equation. So our c becomes equal from 0 to pi on 2, then sine t, then this whole term lambda c sine t, then dt. This lambda c is a constant, can easily bring it out. So I'm going to have c to be lambda c equal from 0 to pi on 2. Then sine t will give me sine square t dt. And we having c here, can divide each of the term both side by our c. I'm going to have 1 to be equal to lambda integral from 0 to pi on 2, then sine square t dt. Now to evaluate this integral, which is sine square, we know that cos 2t will be the same as cos square t minus what? Sine square t. and cos squared t is the same as 1 minus sine squared t. So 1 minus sine squared t minus sine squared t. So here becomes 1 minus sine squared minus what? 2 sine squared t. Now our here becomes that cos 2t, which is equal to 1 minus 2 sine squared t. So we can, let's send this one to the other side, bring this one to the other side. So we're going to have 2 sine squared t to be equal to 1 minus cos 2t. So let's divide both sides by 2. We're going to have sine squared t to be equal to 1 out of 2 to bracket 1 minus cos 2t. Now let's substitute this sine squared t into this integral, and let's solve for our lambda, which is the eigenvalue. So 1 is equal to lambda is equal from 0 to pi on 2. Then half of 1 minus cos 2t dt. Our half is a constant, can easily bring it out. We have 1 to be equal to lambda on 2, equal from 0 to pi on 2. Then 1 minus cos 2t dt. If we integrate 1, we're going to have t. So here becomes 1 to be equal to lambda times 2. Then t, if we integrate cos, we're going to get sine. But the inside is 2t. So if you differentiate 2, then you divide the sine by 2. We're going to have minus sine 2t all divided by 2, evaluated from 0 to what? Pi on 2. So wherever you see t, you replace it by what? Pi. We're going to have here to be 1 to be equal to lambda over 2 pi on 2 minus sine. So pi on 2 times what? 2 becomes what? Pi all divided by what? 2. So wherever you see t, you replace it by 0. It becomes minus 0 plus sine. It's like a 0 divided by 2. Sine pi is the same as 0, and sine 0 is the same as 0. So this whole thing becomes 1 to be equal to lambda divided by 2. Then remaining this term, it is pi on 2. So here becomes 1 over what? Pi lambda divided by 4. So solving for lambda becomes, if we multiply it by 4, it becomes 4 divided by what? This 5. So this is the eigenvalue. And the eigenfunction, which is given as phi of s equal to lambda c sine s. Phi of s equal to lambda c sine s. Lambda is a constant. So all here, constant times constant will give me a constant. You can represent it by another constant. Let's say a u of sine what? S. And so this, solving for this eigenvalue, so this becomes the eigenfunction. So anytime, so this becomes the eigenfunction, and it is a solution to this integral equation, and it's a homogeneous what? Integral equation. Anytime you are given a homogeneous integral equation, and they ask you to find for the eigenvalue and the eigenfunction, you need to use the same process as we did in the exact method in computing for the solution for the integral equations. So this is the end of this session.